Okay, welcome back to class, everybody. It's a pretty good time to get started. So let's just begin by briefly reviewing what we discussed last time in class. So we went over homework 5, so that was the homework on how to route things. So hopefully you saw some useful things in there. In particular, it was your first chance to design your own program structure, right? So you had some chance to think about the class that you want to make, what methods you want to put on it, and so forth. And then we spent a little bit of time discussing homework 6. So at that time, only 3 of you had read the paper. So hopefully today, many more have read it, because those 3 people asked a bunch of useful questions last time, and hopefully the rest of you can step in and ask some useful questions today. And then towards the end of class, we just started implementing minimum spanning tree. So minimum spanning tree was this optimization problem. It was an integer program, but it's very different than the other integer programs that we've been seeing because it has too many constraints. So you can't write them all down at the beginning. Instead, we're going to solve it many times, kind of adding a constraint at a time. And we started programming that, but we hadn't gotten very far with it. And so the plan for today is I'd like to just begin class with a few reminders about the project. So project presentations are starting in just a couple of weeks, and I'd like to say a couple words about that. Then we're going to get into your questions on homework 6. So hopefully more of you read the paper and can ask insightful questions that will help you implement the algorithm. Then we're going to go back to finishing the minimum spanning tree implementation. And finally, we're going to get into scraping web data using Python. This topic was just this topic of there's some useful data online, but it's in web pages, and it's very hard for you to extract into a nice CSV file that you can do analysis on. And there are some Python tools that make this very, very easy, and we'll cover one of them in class. Okay, so let me just begin with the project reminders, which is please, all of you, send me 3 or 4 word title for your project, okay? That way I can take all your titles and send out a final schedule for all of the presentations, okay? So everybody will know what kinds of projects are getting presented in the different days, okay? So that's my main project reminder. My second project reminder is that if your presentation is towards the front of the presentation schedule, please invest significant amount of time to make your project into something complex and interesting that the class can learn from. Because you only get one presentation, and so even if you make your project much more complicated by the end of class, we won't see it, right? We will only see your presentation. So invest the time up front. Okay, so that's it on project reminders. Any questions on the project or homework 6? Yeah.
Okay, so a lot on homework 6, basically.
Okay.
I think I sort of get the meta aspects of what the algorithm, what was being discussed in the paper, but I'm still kind of not really sure how we would go about implementing that. So my sense from talking to you your discussion last time is that we need to find the shortest path between all of the points in the network.
Certainly.
So the destination points in the network.
That's right. So one step that we talked about last time was kind of pre-processing step, right? So here you start with the whole network with all the 100,000 points in Austin. And then we're going to change that into a much tinier network that has only
stopping points.
etc start, etc end, and the restaurants. And also on this smaller network, we're going to have a bunch of data, like extra data that wasn't on the original network, right? So some data that's important on this small network is how resources are getting consumed by going across an edge, right? So in particular, what were our 2 resources? Time and volume. That's right. So how am I going to figure out how much time gets consumed by going across an edge in the small network? It's going to be a shortest path in the big network, right? So in this pre-processing step, for each edge, so in here, each edge has a consumption of time and volume, and each node has a min and a max for each resource. Right, so after I pre-process this, I have all the data for the elementary shortest path problem with resource constraints.
Wait, where are you consuming volume on the edge?
Okay, so great question. So how are we going to do the volume consumption on the edges?
I thought I was thinking there's no consumption on the edges. When you get to the node, then you take off.
Okay, so there's many different ways to do this, okay? So here's one way to do it. Let's say that this is my Hula Hut restaurant node, right?
And sorry, each node has a squiggle for each resource?
Has a min and a max.
Min and a max, okay.
Right, so those are the bounds, right? So Hula Hut has a bunch of incoming edges from all the other restaurants and from ETC start, and has a bunch of outgoing edges to other restaurants and to ETC end, right? And I have to make sure that when I go through Hula Hut, I consume the amount of volume that Hula Hut requires, okay? So where should I put the Hula Hut volume consumption?
I mean, I was with Andrew, I thought that should be on the node, but it sounds like maybe it should.
So in general, like from the elementary shortest path problem specification, those kinds of consumptions are on edges. And nodes have just mins and maxes.
You know, like the incoming node or the incoming edge.
That's right. So you could put the volume consumption here. Right, so if I put it on all these incoming edges, then what's going to happen is, regardless of where I come into Hula Hut, I have to consume the Hula Hut's volume, right, to get there. So that's one option. So I'll just call that option 1.
You could also do maybe what we did last year where you have like a split node.
Yeah, exactly. So that's another option, which is kind of like what you guys were saying, which is consume it at the node, right? So another option is have Hula Hut start, Hula Hut end, and have all the incoming nodes be in here. So these consume time, but not volume, okay? Then we have a single edge that goes from start to end of Hula Hut, and that single edge consumes volume only, but not time, right? So then this one consumes volume, but not time. And then these outgoing edges, again, just consume time. Okay, there's a third option.
I think we just do it inside the extend function and have that kind of like automatically.
You could potentially do that, but it's a little hacky. So it's not quite implementing the algorithm, but there is an option there of doing something like that, and it's probably equivalent to one of these two things. Because probably what you're doing is your extend is, instead of extending from this node to this node, you're actually extending this way. Does that make sense? Because you're consuming the time and then the volume, which is also exactly equivalent to this, because you're consuming the time and the volume when you extend. Does that make sense? So what's a third option for placing the volume consumption for Hula Hut? That's right, yeah, I could put it on the outgoing edges of Hula Hut, and that's just as good, right? So here's my third one.
I think I missed your explanation for what the min and max are. There's a min volume you have to take.
So in the problem specification, it says that each node has a minimum requirement and a maximum requirement for each resource, okay? So for time, that would be like a time window. Like you have to get here after 10 and before noon.
Okay.
But you could do that for any resource, right? So it could be the case that Hula Hut consumes 2 volume, but requires that you have between 15 and 30 like in your truck. So so it doesn't, for volume, it doesn't make as much sense as time. But in the problem specification, every resource could have these lower and upper bounds. Yeah. So our last option was to put the volume here. So volume consumption. Okay. So I think that answers the question on where to put the volume consumption that you guys had. So other questions, yeah.
So that time window, is that just when you have to show up? So the time window is 10 to 11, you can get there at 11 and that's fine?
That's right.
Okay, I figured, okay.
That's right, okay. So that's a great question, and the way that we're going to interpret it for the homework assignment is, that's just the time at which you get there, okay? But let me ask you a slightly different question. Suppose that what it actually meant is that suppose that like loading and unloading took some time, right? So let's say it took half an hour to like unload whatever it is. And the time window, 10 to noon, means that you both have to arrive within that time window and you have to be done loading and unloading within that time window.
Probably still just shift it so your arrival time is like 10 to 11:30.
So that's one thing you could do, or another thing you could do is this split, right? And then this could be your half-hour time consumption, and then this could be like the same time window, right? So many options there again, but it's just again a question of how you connect the real-world data to the actual mathematical problem specification. Other questions?
Same time window, right? You will have to adjust it according to the loading times, right?
So I would consume half an hour here, and then here I would still have the same one. So why doesn't that work?
So if you have the same time window, and say it's 11 to 12,
Yeah.
that means that you can arrive at 10:30, right?
Yeah.
There, but you have to arrive between 11 and 12.
So, but I'll be consuming half an hour here. So I can arrive at 10:30, but then here.
It's okay to arrive at 10:30.
Yeah.
Even though the time window is actually 11 to 12.
So, okay, so what happens, so that's a great question. So what happens in the paper if I'm, let's say at ETC, okay, but the first lower, like if I look at all the restaurants, no restaurant allows me to get there earlier than 10, but I can leave at 9. So what happens when I do extend at that point?
Because there's just like you're waiting. So
That's right. That's right. So you add the amount that you need to get there within the lower bound, right? So, but you're going to get there just inside the lower bound.
And the other thing is, so when we are pre-processing, we find the shortest path, shortest time path, right?
Yep.
But that sort of prevents us from those solutions which are not shortest time path, but might be better in the resource constraints, right?
Which resource constraint?
Like, for example, volume or time. Volume here.
The only thing that matters when we're doing the pre-processing is the time, because at that pre-processing step, like, volume just doesn't matter. Because the only thing that matters, the only place where volume matters is when you're deciding the order in which to pick up and drop off from the restaurants, which happens after pre-processing. Other questions? Yeah.
The objective function is just multiplicative, right? The value times the volume?
No. So the value is, so if I'm dropping off 12 and the value is 1, you still just get 1.
You just get 1.
Yeah, you just get 1. So the value is for going to that restaurant at all, if that makes sense. That's right. That's right.
The way you described it, so like at the end, say we'll have 10 labels on the end of it. So then we
Yep.
can look at it and we pick the one with the highest value at the end. Is that
That's
correct?
right. Yeah, that's right.
Other question, it seemed like that EFS function, the one that shows you what's dominated, is going to be the time filler. Do you have any recommendations for that?
Yeah, not in particular.
Okay.
So the algorithm is intended so that you basically like kick out dominated labels as early as possible, right? And so that's the thing that's going to save you time, is to be kicking out labels from your nodes as soon as you find that they're dominated by some other label. But other than that, not very much can help you make that faster, I don't think.
You have to do like individual comparisons.
That's right. Absolutely, individual comparisons. Unless you come up with some hyper-intelligent vectorized way, but my code certainly did not do that. Yeah.
Can you explain dominated and non-dominated?
Okay, so that's a great question. So what does it mean for one label? So what does it mean for label 1 to dominate label 2? So first of all, what is a label? So in the algorithm, what defines a label?
Is now whatever optimal solution we have found, like not actual optimal, but whatever is the best solution we have.
So it's not really a best solution that we have.
Maybe the reachable.
So does somebody else want to try? Like, what's a label?
So it's a label, so it's describing, first of all, like the amount of resource, so it's the path from the beginning to some node I.
So path so far, right?
Path so far, and it's, the resources you consume, so here that would be time and volume.
Okay, so so let me just clarify a little bit before you go on. So path so far. So labels are on nodes, okay? So if this label is on node I, the very last thing on the path so far is going to be node I, because I know that I took some path to get here, okay? Now, the rest of the label, so it has this, but the rest of the label has some information about that path, right? So what other information about that path does it have?
The first is the resources you consume, so here would be volume and time.
So the amount of the resources consumed so far, right? And there's, amount of resources consumed so far. Great. So I can calculate that by looking at the path, but I actually don't calculate it by looking at the path. I calculate it iteratively as I'm extending these labels, right? But go on. What else?
Then it's a count of the unreachable nodes.
Yep. So, go ahead.
For each node, a 1 or a 0, 1 if it's reachable and 0 if it's...
How about, let me just write that as the set of unreachable nodes.
Unreachable.
That was my next question. What does unreachable mean?
It's either you've already been there or you don't have enough resources to get there.
That's right. So two things. Either I've already been there, and why is it unreachable if I've already been there?
It's already in your path.
Yeah, because it's an elementary shortest path, right? I'm not allowed to repeat a node.
How
So,
do you make that instruction
which?
that you cannot repeat?
The labels also.
Yeah, so the labels keep track of what's unreachable, and you're never going to extend a path to an unreachable node.
Okay.
So that's what makes sure.
Separate attribute or something?
Which?
Like if you've already been to something, you.
Oh yeah, that's the set of unreachable nodes is a part of a label definition.
Right.
So when I'm looking at this label and I'm looking at how can I extend this path, I'm never going to extend it to an unreachable node.
Right. Okay.
So unreachable node. So let me sort of clarify what that means. Is we've been there,
Right.
or the other thing that could make it unreachable is that we don't have the resources to get there, right? Okay, so this is what defines a label. And actually, the count of unreachable nodes, you can, like this is actually information that you already have if you are maintaining the set of unreachable nodes, right? So maybe I can erase this one to just simplify things a little bit. Okay, so I have two of these labels. So they're both on node I, label 1 and label 2. They're both on node I. when does label 1, okay, there's one more thing actually on a label that we haven't done yet. So what is the last thing on a label? The value, right? So the last thing here is the value of the path. Okay, so these are the four things that define a label. So now I'm looking at node I. It has two labels. How do I know that label 1 dominates label 2?
Basically, if it's used less resources, has like maybe fewer unreachable nodes or something, and then also the value of the path is like it's less, the cost is less, all those conditions in that.
That's right. So let's clarify fewer unreachable nodes. So the first two things that you said are right. So label 1 dominates label 2 if it has a better value, right? So better, since we're minimizing, we're going to say smaller value. But even though we're actually maximizing profit, and we're just going to make those values be negative, right? So smaller value than label 2. Also has consumed less resources, right? So less resources than label 2. But what about set of unreachable nodes? So it's not quite fewer.
Doesn't matter. It can be any number of nodes, right?
So not quite.
It's so I guess the dominant solution,
So
its unreachable nodes will also at a minimum be in the denominator.
yeah, so you said that right, but let me say it in a slightly different way, which is that the set of unreachable nodes in label 1 is a subset of the set of unreachable nodes in label 2, right? So it's like a bunch of less than conditions, right? So like label 1's value is less than label 2's value, and maybe we'll make that less than or equal to. Label 1's resources is less than or equal to label 2's resources, and label 1's unreachable is a subset of, so these are less than or equal to signs, and label 1's unreachable is a subset of labels 2's unreachable. It probably does, and it's probably a on to the set type object that we learned at the beginning. I store them as sets when I implemented things, but you can do it whichever way that you like. So why does it make sense that why did people define this domination relationship? Like, why does it make sense in terms of the algorithm? The reason it makes sense is because it's essentially saying that there is no way that the path from label 2 could possibly be better than the path from label 1, right? Even though it's partial and we haven't completed going to ETC yet, there's no way that it can be better because I'm getting a better value, consuming less resources, and have more options of where to go from here than the other one, right? And so if label 1 dominates label 2, I can just drop label 2 from the node and pretend that path doesn't exist, right? Because there's no way that extensions of that path could possibly be optimal. Yeah.
We have to add one more condition that they are not actually equal.
That's right. Yeah. Oh, absolutely not. No. You can do it in whatever order you want. Oh, yeah. That's right. So domination isn't like a total ordering of labels, right? It's not that either label 1 dominates label 2 or label 2 dominates label 1. It's possible that they're incomparable, right? That like you can't say which one dominates which of. In that case, both of them have to stay. That's right. Yeah.
So just to clarify, label 1 and label 2 are two different paths so far from their origin to the current node.
That's right.
And then I think what I confused them a little is in the paper they said something about that we will from now on consider only the non-dominant labels?
That's right.
So why, if label 1 is better, if label 1 is dominant, and that, because it has a lower cost and uses less resources, that's what we want, why are we considering the non-dominant?
So non-dominated labels. So that means that every label that's dominated gets dropped. So label 2 is going to get dropped.
There's not dominated, not non-dominant.
Yeah.
Sorry.
Question back there? So other questions? Yeah.
I just had one clarification. So, line 12 and 13 of their algorithm, first we have a for all, so basically for all labels in the labels possible, but then it says like do if for like the shades that are 0. It seems like that should also be like another for loop, right?
So I actually, when I implemented the algorithm, I did not follow their pseudocode.
No.
I sort of did my own pseudocode that's totally different from theirs.
But in theory, we need like every ij pair that's reachable.
That's right.
Okay.
So in particular, you're probably talking about, so the one thing that we haven't talked about so far is like extending, right? So how does this algorithm work overall? Let me ask you that question. So we now have labels, we have the idea of nodes and how to populate everything, but how does that algorithm work overall? So can somebody explain the algorithm to us overall?
Scan the successor node for non-dominated labels. That's the first algorithm.
So I have a bunch of nodes here. Right, this is my compacted network that only has the restaurants. I have a bunch of edges between them. Right, and in fact, every pair of nodes is connected, right? Except this is etc start, and etc end is here somewhere. And this has a bunch of edges going into it. That's going to be our final node, right? And each node has a bunch of labels on it. So label 1, label 2 of this node, label 1, label 2, label 3, and so forth. So each node has this list of labels on it. So how does the algorithm actually work?
We have this set E that's nodes we have to deal with.
Okay, so we have a set E that's sort of nodes. So you said we have to deal with, but can we say that in a slightly like more clear way? So what's the set E actually hold?
This list of nodes waiting to be treated.
So that's what they're, but what does it actually mean from your understanding from the paper? So those are nodes that have a label that we haven't tried extending. That's what it means, okay? So these are nodes that have a label that we have not tried extending. Okay, so you can think of a label as being in one of two states. Either we've extended this label previously or we haven't extended it ever, right? So for example, let's say that we just start with label 1 on the start here, right? So at the beginning of the algorithm, we just start with a single label on etc. And then what's inside of E? It's just a single node, that's etc start. Because etc start has one label that we haven't tried extending, which is this one, right? So then we're going to go and extend that one. So let me denote that we haven't tried extending a label with a little dot above it, okay? So we haven't tried extending this, so we're going to go and pick any node that has a label that we haven't tried extending, which is this one, and we're going to go and extend every label in there, okay? So here it is. We took that label, and then we extended it, which gave us a label here, and it gave us a label here, and it gave us, so those are the only two edges out of etc start, okay? But since these are new labels, they have a dot on them because we haven't extended them previously, right? So now what's in E? It's this node and this node because they have labels we haven't tried extending, right? So now I can pick an arbitrary one out of there, like this one, and then extend all the labels that are in there, right? So I'm going to go in here and extend this label, and now it's been extended, but I'm going to add a label here, label 2, because I'm going to extend across this edge. And label 2 also hasn't been extended before, so it gets a little dot above there. Yeah.
Why not all three edges coming out of EPC?
Oh, I just overlooked this one. So you're right. That this node would also have a label on it, because these labels get extended in every direction which it's possible to extend them. Okay. So how do I figure out what directions are possible to extend for a label? I just look at the complement of the unreachable set, right? Because all the other nodes in there should be reachable.
There should be an outgoing node from PTC star to every other node, right?
Yeah, that's right. And so I didn't draw the edges here because it's a little complicated to keep track of. But so that's kind of the basic idea of the algorithm, is you keep picking nodes with labels that haven't been extended, and then you go to that node, and you extend every label on that node that hasn't been extended, okay? And so when I pick a node, I kind of, I clean that node out. At the end of it, it's not going to be in E anymore. But it could have created new nodes that are in E, right? So then I go again, and I pick another node that's in E and extend all the labels in there. So at each iteration, I'm removing one node from E, but potentially adding lots of other ones. But the thing that's going to help me not add too many nodes in E is this domination criterion, right? Because if I extend to a place, but the label that I'm extending is dominated by some other label at the place that I'm extending to, then I'm not going to add that label. Does that make sense? So for example, if this label 2, which came from the top node, was dominated by label 1, then it's not going to get added on there. Does that make sense? So that's kind of the overall idea of the algorithm. So ask your question again if you still have it in terms of what the pseudocode means.
Okay, I just wanted to make sure, yeah, so for each label in a node, we need to look at then each place from that label we can possibly go.
That's right.
Every label direction combination.
That's right.
Okay.
That's right. So every label, when you're extending it, has to get extended in every direction that you possibly can extend that label, right? Okay, so let me ask you a quick question. So suppose that this is like the 500th iteration of the algorithm. So we have like labels all over the place, okay? This node has 3 labels on it, L1, L2, and L3. L1 and L2 haven't been extended previously, but L3 has. So this node is in E because it has some labels that haven't been extended. So suppose that I pick it and I go to extend. I extend L1, I extend L2. Do I have to extend L3? No, because I already extended it before, right? Now, and if I extend it again, I'm actually going to get the exact same labels that I would get the previous time I extended it, right? And so once you've extended a label, like, you're never going to extend it again. Does that make sense?
What is there? Will that hold even if they are non-negative cost, right? It will hold even then.
Yeah.
Negative cost.
Once I've extended a label, I'm never going to extend it again because I'm going to get the exact same labels on the other end.
But suppose if there is a negative cycle,
Okay.
and we could still decrease it till we have
It's
a-
elementary shortest path though, so cycles don't matter. Okay, other questions? Yeah.
This is, I guess, more of a mechanics question. Did you use, when programming, did you use like Network X to help you model nodes and edges and then make your own
I think I
algorithm?
did.
And
Yeah.
then just kind of write maybe like your own algorithm function? Or?
That's right. I think I did. I used Network X to hold this stuff. And I probably used dictionaries on Network X to maintain the labels on each of the nodes. And then I had my own sort of elementary shortest path function that did the for loops looking for, it probably had something like while E is not empty, right? Because that's when the algorithm ends, when you've pushed everything out of E that you can.
And then, rather than using like Pyomo to make constraints, you kind of enforced your own constraints.
Yeah, there's no Pyomo here anywhere, right? So the constraints actually are coming from the way that we define the labels and the way that we're defining label extensions. So the constraints are kind of like built into the algorithm. And that's partly the reason why I'm having you guys implement this paper, because it doesn't rely on a pre-existing solver, right? So it's not like we're just using Cplex or Gurobi or something. We're doing a custom optimization algorithm, the same way that we did with stochastic gradient descent, right? So from scratch, like your own optimization algorithm that's specific to this problem. Other questions? Yeah.
Is it possible to remove more than one node at each iteration from each?
No. So in each iteration, it's going to be one node that you're going to remove. So there is like you could potentially doctor data in such a way so that when you extend, you dominate all the non-extended labels on some node, okay? In which case you might drop multiple nodes from E, but that's like a tiny optimization on top of the existing algorithm. So the way that I implemented it, I only drop one node from E in each iteration, and you're not going to have any slower of an algorithm to do that. Other questions about the homework assignment? Okay, if not, I think that I really think that this is a pretty thorough view of the algorithm overall. So you know the pre-processing step, which is creating that small network and how to put data on it. You know what labels means and what it means to dominate labels. You know an overview of the algorithm in terms of picking a node that has non-extended labels and then going and extending all the labels. The one part that maybe we didn't talk about was extending a label. So how do we extend labels? So if I'm extending from this node to this node, you know, I take this label and how do I create the new label on this one?
Add up all the
So I look at the resource consumption, right? So I have to add the resource consumption on this edge, and I might potentially have to add an additional amount to make sure that I'm greater than the minimum over here, right? So that fixes my amount of resources consumed. I have to edit the path to add this new node to it, right? I have to edit the value of the path because I've now reached a new node. And then maybe the most interesting part is the set of unreachable nodes. So certainly I'm going to add one more unreachable node, which is this one, because I just visited it, right? But I might potentially add lots of other unreachable nodes. So how do I add other unreachable nodes to here?
the outgoing node from this node.
That's right. I look at the outgoing edges, and I see across which of those edges I can extend, right? And if I can't extend across that edge, that node goes in the set of unreachable nodes. Does that make sense? So when you're extending this label, you're actually going to look at both this one edge that's going into this node, but you're also going to look at the outgoing edges from this node to update your set of unreachable nodes. Make sense? Okay, unless there's any further questions, I'm going to move on to talking about minimum spanning tree, which is where we left off at the end of last class. So let's just briefly remind ourselves where we were. So this was our integer program for minimum spanning tree. We had some variables, yij's, that tell us whether an edge was on the minimum spanning tree. We had an objective function which was minimize the cost of the spanning tree, which is just Cij times Yij. And then we had two types of constraints. So one of these constraints was easy, but the other one was hard. So the easy one was just that the sum of the yij's have to equal to n minus 1. But the hard one was this one. And the reason it was hard is because we have to write a constraint like that for every subset of the nodes, which is too many of them, okay? So let's remind ourselves also how far we were in terms of programming this. So in terms of programming this, we read in the CSV file, we computed a node set out of that. We started our Pyomo model. We computed an edge set. And then we added that edge set to the Pyomo model. We defined variables, which was 1y for every edge in the edge set. We defined the objective, which was just the y's times the cost of that edge. And then we added that simple constraint. So that's where we ended class last time, was adding the simple equals n minus 1 constraint, which is just the sum of the y's over the edge set equals n minus 1. Okay, so what's the plan on how to deal with the complicated constraint? So the basic idea is that we're going to start solving this problem without having any of these constraints in there, okay? We're going to have nothing at the beginning. We're going to solve it, and we're going to get some kind of a graph out. Some of these y's are going to be 1s, n minus 1 of them are going to be 1s, but I might potentially have loops in there, okay? And for every loop that I have, I can remove that loop by adding a constraint like this, by saying the sum of the y's over the sets over the nodes in that loop has to be less than or equal to the size of the loop minus 1. Does that make sense? So let me just give you a picture example of that, what that might look like. So let's say this is our graph with 4 nodes, and the first time we solve it, we get this, right? So this is not a spanning tree. And in particular, it's not a spanning tree. The sum of the y's is equal to 3, but it's not a spanning tree because when I look at this set of nodes, that set of nodes doesn't satisfy a constraint of this type, right? And so I'm going to add a constraint that looks like that to the problem and then solve it again, okay? So let's try to program that in Pyomo. Yeah.
Will you add a constraint just for that particular thing or for the whole, like here in this case, a subset would be a three node set, right?
Yeah, so that's a good question. So let me draw this slightly differently. So suppose that what we got was this. So our graph had 5 nodes in it, and the first solution that we get is this, right? So it has 4 edges in it. I'm going to add a constraint for this connected component. Okay? So not for the loop only, but for the whole connected component.
What I actually wanted to ask was, like, so if you just add it for that particular 3 nodes, then next time the solver could spit out a loop like this, right?
Oh, yeah, absolutely. So it's not going to be only one iteration. It's going to be potentially many iterations.
Yeah, so to avoid those iterations, we could add a constraint for all the 3 subsets.
Right, but what's the problem with that? Why don't I add the constraint for all?
Make it more
That's right. So I only want to add kind of the important ones. So that's why I'm going to add them one at a time.
Are you just going to eyeball the cycles in the graph?
No, we're going to find, so we're not going to find the cycles, we're going to find the connected components. And there's a very fast algorithm to find connected components in a graph. Okay, so
we could use sorted path also for finding the constraint.
so it's variance, like in particular you can use DFS to find connected components. So I'm just going to have a variable here that says done. It's like, are we done solving this problem? And while not done, we're going to do the following. First, I want to actually solve this. So solver is going to be p.opt pyomo.opt.solver factory cplex. And all I want to do here is just say solve the model that I have so far, okay? So I don't always remember exactly what these lines of Pyomo look like, so I'm just going to look at our all facility location code here to get the solver lines, and here they are. So I'm just going to copy these two lines that solve a Pyomo model. So I get the solver, and then I want to solve our model. Okay, so at the end of solving this, I'm going to have some values for the y variables. Now, I want to figure out what are all the connected components in the graph based on those y variables, because each connected component is going to give me a constraint that I'm going to add to the problem. Okay, so to do that, we're going to use network X connected components. Okay, so we can read that this algorithm here. So generate the connected components as subgraphs. So I'm just going to use this network X function, and it's going to return all the connected components as subgraphs. So, but the first thing I need to do is take the y's that come out of the Pyomo model and create a network X object out of them, right? Because before I can call this function, I need to have a network X object to pass into it here. So help me write some code to do that. So here's a function. It takes in a model, and I want to look at that model's y's to create a network X object. So how do I do that? Say again? Yeah, so let's say the answer is going to be network X.graph. So graph instead of digraph, because we're going to do minimum spanning tree on just graphs instead of directed graphs. Okay, so that's my answer, but right now it's an empty one. So how do I fill in its edges?
Are we just adding the ones with y equals to 1?
Yeah.
So just like for I in model dot y.
Not quite.
So I'm just writing a one-line statement instead of a for.
Okay.
So for E in LZ, if y is equal to this, you can use a list comprehension and assign it to.
So you can't iterate over the y's, though, I don't think.
I did that in my.
Okay, so how did you do it? Yeah, maybe I'm going to learn something. So what did you do?
So my second was something like for I in model dot y, if model dot y equals to 1, and then use the list. So I will become a list. So I for I. So using a list comprehension, so you have to add some set is equals to I. Yeah. I.
Okay, I'm not sure that this is going to work at all.
It was something like that.
I'm highly dubious, right?
I'll use this number.
But let's give it a shot.
Like this,
So
like so you have to index the edges. So you have to index the indexing part is there.
So I just want to look at m dot y just to make sure that we have some values for it, but we don't. Okay, so I ran cplex, so now if I look at m dot y pprint, I actually have some values for the y's. And then
Instead of model.y, we have to use the edge set of model. So
so we're going to iterate over the edge set.
we don't need to use value here.
Okay, so you want to just say y, and then here I just want to have e or something like that. Okay, so let's see if this works.
That's m dot. So m dot is not model.
Okay, so what are we getting? AD, AB, AE, and BD and BE. Okay, looks great. Fantastic. Okay, so now I have here my edges are going to be these things. And then how do I add them to the graph? So I think that's going to do it. Okay, so going back to our for loop. So here we have, we're solving the model. And then we're going to get the graph is going to be equal to convert y's to network x. We're going to pass in m. And then we're going to call connected component subgraphs. So connected component subgraphs of G. Let's just make done equals true, and then just for connected component and connected component subgraphs, let's just print the connected component nodes. So I'm just doing a debugging step here. So it's telling me that at the beginning, the connected component is created from the nodes A, B, E, and D. Okay? And why is that? Because if I look at the edges that are in our tree, it's just AB, AD, AE, BD, and BE, right? And so that's the one connected component. So now which...
One question. So this function, does it give, like, if we have two connected components which are disconnected, it will give all the those components?
That's right. It's going to give a iterator over all the connected components. So here there was only one, so that's why we only got printed one. But if there were two, it would give us two. Okay, so what constraint do I need to add now to our Pyomo model?
So for each of the connected components, we can add...
Yeah, the sum of the y's within that connected component has to be less than or equal to the number of nodes minus 1, okay? So let me define another function here, which is create constraints for a connected component. It's going to take in a model M and a connected component CC, and it's going to return a Pyomo constraint, okay? So help me write this constraint. So what is this constraint going to look like? So CC is a connected component, something like the nodes A, B, D, and E, right? So it's a set of nodes. And so what does this constraint, what should this constraint say? Sum of the y's that are all within this connected component has to be less than or equal to the number of nodes in this connected component minus 1, okay? So help me write down the sum of the y's that are all within this connected component. So here I'm summing over all the edges in y, but I want to make sure that they're in the connected component. Not quite, not E and CC. So I want to write this. So why did I write this instead of E and CC? So what did I just write? So I'm looking at an edge E that's inside of the model, right? And I need to make sure that this edge is inside this connected component. How do I know that the edge is inside this connected component? If both its start point and its end point are inside the set of nodes in the connected component, right? And that's what this condition is checking, that the start point of the edge is in the connected component and the end node of the edge is in the connected component. But if the connected component is a list, like 100 nodes, how fast is this? Yeah, because it's like a little for loop that's iterating 100 times. So how can I make this a little faster? Turn it into a dictionary. Because now the lookup is going to be a O of 1 time lookup instead of iteration over a list. Okay? So I want this sum to be less than or equal to what? And that's what I want to return, right? So let me do something else here. So instead of, in addition to printing CC, let me print create constraint for CC, passing in M and this connected component, and run it to see if it's creating the right constraint for our first iteration here. Okay, so the connected component that we got was A, B, E, and D, and the right-hand side looks right, it's 3, and here we're getting DE, AD, AE, AB, BE, and BD. And that seems right? And just to kind of double check with m.y, so the current solution makes 5 of these be 1, and only 3 of them can be 1, right? So by adding this constraint, the next time that I'm going through the loop, there's no way that I'm going to get this solution out. Does that make sense? And so every time through the loop, when I get a solution that's not right, I'm going to add a constraint that eliminates that as a future solution. Does that make sense? Okay, so the last thing that's useful here is a constraint list. Okay, so a constraint list is just a list of constraints that you can add sort of one at a time in the way that we need to add it. So at the beginning here, I'm going to add m.cc constraints is going to be Pyomo constraint list. And Constraint List has an add function that lets you add constraints based on a expression. So here I'm going to print the nodes, I'm going to print the constraint, and I'm going to do m.cc constraints add this thing. Okay, so when am I going to be done? So before I deleted the last line here, I just said done equals true because I wanted to go through this loop just once, just for debugging purposes, right? But to actually solve the problem, I'm going to go through this loop multiple times. So how do I know when I'm done? Yeah, that's right. When the connected component is the graph itself, right? So how do I check that? So if some condition done equals true, right? That's kind of what I want to write. So how do I check if the connected component is the graph? So first I should be getting exactly one connected component. That's the whole graph, right? And what else? So that's not quite enough. That's right. That's right. So the number of nodes in that connected component has to be equal to the length of the node set. Right? At that point, I should know that I'm done.
Why do we need to, like if we ensure this, we know that the solution gives us a connected component. So if we just check this, this is not required, right?
Yeah, that's true. This is not, yeah, the first one's not required. Okay, so let's run things and see what happens. Okay, so the issue is that connected components is a generator and not a list. So here, I'm going to turn it into a list so that I can refer to the 0th number of it, the first number, and so forth. So you guys have probably run into generators before, right? We've talked about them previously. Okay, so let's take a look at the connected component 0, the edges. So these are the edges that came out in the last connected component, the thing that told me that the algorithm was done, right? And let's compare it with the minimum spanning tree answer on Wikipedia. Right, so this was the example that we had plugged in. And the edges that we're getting is AB, AD, CE. So AB, AD, CE, and then we should be getting BE and CF. CF and BE. So we did actually get the minimum spanning tree, or one of the multiple minimum spanning trees that are out there. And also let's look at our model. Okay, so it has the edge set that we created, the objective function we created, and then the two constraints. The simple constraint was right here. But let's see how many connected component constraints we put in there. So it looks like we put in 3, right? And how many constraints are there in that graph? Well, there's 6 nodes. So there's something like 2 to the 6 constraints if I'm doing it for all possible subsets of the nodes, right? And so that's one thing that you commonly find with these row generation type algorithms, is that even though I have an enormous set of constraints here, as I'm doing the row generation, I don't actually have to add in all of them. I only have to do a relatively few numbers of iterations to get the right solution out. And for those of you that know a little bit about LPs, it's because I have relatively few y variables. So in an optimal basis, I can't have too many constraints active either. So if I somehow pick just the right constraints, then I should be able to solve this to optimality. Okay? So the main kind of learning bits from this example is really this idea of iteratively adding constraints to your model and solving it over and over again. So this is something that comes up again and again and again in operations research algorithms. Probably hundreds or thousands of papers written on this basic concept of solving an optimization model and then adding a constraint to it at a time. Okay, so any questions about that? Or any confusion that you may have had from what we just did? Okay, if not, then let's move on to talking a little bit about scraping data from the web. Okay, now let me just set up the problem, and we probably won't get to programming it very much today. But in terms of setup, let me just give you an example. So this is just an arbitrary website that I picked. So there's various OR people that blog about operations research. And so this is a complicated website where this person is sort of putting up all kinds of information about their recent blogs. So lots and lots of text and so forth. But suppose that the analysis that we want to do is to pull out the dates of his blog posts and the titles of his blog posts, because I want to do something like measure how often this person blogs, okay? And maybe like my analysis should be something like, is the frequency of this person's blogging related to some other events, okay? But this data is like very, very difficult to pull out from the web page by just looking at it, right? So it's not like a nice CSV file. If you didn't know about web scraping, you might think that the fastest thing to do is kind of like write it down or cut paste yourself from what's on there. Moreover, this initial page of the blog only has about 5 or 10 blog posts. And then here we could click on older posts, and then it brings up another page with more blog posts, right? And then at the bottom of this, there's another page with more blog posts. And so if I want to get the last 100 posts that this person has, I might have to do a tremendous amount of clicking and moving from one page to another to collect the information that I want to collect, okay? So the tool that's going to help us collect this information is not a module, okay? So far we've learned a lot about different modules like pandas and SciPy and so forth. But to do this data collection, we're going to use a tool called Scrapy, okay? So Scrapy is more than a module in the sense that it's a module with several programs that are developed by the module creator. And those programs make it particularly easy to do this web scraping. So just to give you an idea of what makes Scrapy different than a module is that instead of the typical thing where we start a Python program and we write import Scrapy or something like that into it, here on the command line, you would do something like Scrapy start project, new scraper, okay? And by doing that, Scrapy creates this directory, new scraper, with a whole bunch of files in it, okay? So that's kind of the beginnings of writing your program that's going to go to the web and collect this data for you. So I've already done this before for the OR blog. So to do that, I just did Scrapey start project OR blog. Okay, so a Scrapey project has a number of spiders. So a spider is one of these programs that's going to go off to a predefined website and take out the data from that website that you want to get. So for the OR blog, so this is the directory that Scrapey created, and inside of that directory there's a spiders directory. So if we go into spiders, there's some default files in here like the init, but post spider is a program that I wrote that defines the data that I want to pick up from the OR blog. So let's take a look at post spider to see what its contents are. Okay, so when you're writing your spider, that's when you actually use Scrapey as a module. So all of this is code that I wrote, and you would write sort of the equivalent but slightly different code for whatever data it is that you want to collect from a web page. So at the beginning, you import Scrapey, and then to define your spider, you call it whatever you want, but it has to be derived from the Scrapey.spider class, okay? So Scrapey.spider is a class that the Scrapey people wrote that has a lot of functionality in it, okay? The second thing that you want your spider to have is a unique name. So if you have multiple spiders, each of them has to have a different name on it. And for me, I decided to call this one posts, okay? So and this is how you set a name for your spider. The other two key parts of a spider is a function that tells it where to start, right? Because at this point, Scrapey doesn't know anything about what web page I want to collect data from. And the second key part is once you tell it where to start, some program to tell it which information to collect from that web page, okay? So let's read this first part that just says start request. So this just tells my spider on what web page to start. And here I've done some things that are specific to my particular spider. So in my particular spider, I want to make sure that I don't collect more than 45 of his recent posts, because otherwise it would just keep going and collecting like all of the posts on the blog. But I just want the 45 most recent ones. And then I want to specify the location of the web page in which I'm going to start. So that's what this URLs is. So that's the location of the OR blog that I just pulled up. And then let's take a look at this other part. So for URL and URL, so I'm going to iterate over this list. I'm going to do what's called a yield Scrapey request. So that means sending your spider to that particular URL. Send the spider to this URL, and when you retrieve that URL, call this function, okay? So it's going to go and collect the HTML from that web page, and then it's going to call self.parse with that HTML, okay? Does that make sense? So let me ask you a question before I move on. So are you familiar with yield? Have we talked about what yield does before? Okay, so let me just give you a quick tutorial on that. So let's do something like this. So let's just define a function. Let's take n, and it does something like for I in range n, yield I. So this has nothing to do with Scrapey. It's just some fundamental Python syntax that you're not familiar with yet. So you can think of yield as a type of return statement, but it's a return statement where if you call the function again, it's going to keep all of the context of that function up until that point. So the first time I call that function, it's going to return 0. The second time I call that function, it's going to return 1. The third time I call that function, it's going to return 2, and so forth, all the way up to n, at which point if I call it again, it's going to give me an error. So, but more accurately, it does the following. Okay, so let's say that I call afunc with 10. What it actually returns is one of those generator objects that you've been familiar with in terms of using other people's modules or iter tools and so forth, right? So it returns a generator. And this generator has a next method on it. So when I call generator.next, it's going to return the 0. When I call generator.next, it's going to return the 1, then the 2, the 3, the 4, all the way up until we get to 9. And then at the 10th call, it's going to call stop iteration. Okay? So what that allows me to do is things like this. For I in afunc 8, print I. Does that make sense? So afunc returned a generator that iterated over 1, 2, 3, 4, all the way up to 8. And this iteration is going to stop when this generator stops generating things. Does that make sense? So a similar thing is happening here with Scrapey. This is returning a generator that's yielding URLs. And somewhere inside the Scrapey code over here, inside of scrapey.spider, there's a for loop that looks like something like for URL in start requests. Okay? And that for loop is going to go through every URL that you yield over here. Does that make sense? In this example, I'm just yielding one URL. So let's stop here, and we'll pick up from here next time on how to actually extract the data from the URL that we've started on. So thanks a lot for listening, and I'll see you all next week.